Hello everyone, I'm Dr. Meena, Assistant Professor, Department of Mathematics from KPI Institute of Engineering and Technology. Today I'm going to present how mathematics are applied in electrical engineering. So here we are going to see the mathematics is the fundamental tool which analyze a complex electrical systems. So this mathematics behaves as a bridges between the modeling circuits as well as with the real world technology. So many of the engineering students will come across the mathematical problems in their field, especially in the electrical engineering. We are having so many concepts that are applied. So in this video, the first concept we are going to see is in circuit analysis and network theory. So the large circuits with the dozens of components are solved by using the system of linear equations. So we can solve the linear equations by using the simultaneous method or by any of the rule, but all these equations are applied in the circuit analysis as well as in network theory. So linear algebra is the engine which is used to stimulate these circuits. And the students will be come acrossing about the complex numbers, and these complex numbers are applied in AC analysis. That is, the complex numbers simplify the steady state analysis and it turns a difficult calculus into manageable algebra. And the next is we can see in electromagnetic field, we can apply the vector algebra. So for example, in designing the antennas for smartphones or the wireless charging pads, it requires the calculating how electric and magnetic fields propagate through the space. So understanding all these curl of vector fields, it is essential for these calculations. The next topic we can see is in signals and systems. So everybody knows as an electronic students as well as in electrical engineering students, they'll be come acrossing about the frequency domain. In this frequency domain, the mathematical concepts like Fourier transforms, Laplace transforms, and Z transforms are applied here. So in general, the mathematical transforms allows the engineers to see the signals in the frequency domain. Fourier transforms separates noisy radio signals from actual music. It also used in filtering also, that is especially the Laplace transforms, it determines the system's transfer functions in designing the filters to remove the static from the phone calls. So in this way, we can use the mathematical transforms in signals and systems. So it will be used mainly for the electrical engineering students as well as the electrical and electronics engineering students. The next thing is we are going to see in control systems. So normally in the control systems, we mainly use the differential equations. So the control theory, it ensures the system stability. For example, we can see the drone movement. A drone's flight controller, they use the proportional integral derivative algorithm to check the level of the drone. So here we use the differential equations and we can analyze the drone flight is under the control or not. In this way, we can use the systems like in robotic arm, it will move smoothly or vibrate uncontrollably. So especially in the stability analysis also, we are using this control systems as well as differential equations. And the next one is we can see in power systems. So for example, in the power flow management, that is managing a city's power grid, it involves solving a non-linear algebraic equations to ensure every home it gets the right voltage. So in this way, throughout the city, equal amount of voltage are supplied in each and every area. Also, we can use this power systems in stochastic modeling also. That is, the statistics model power, it loads and renewable energy uncertainties. So here we can use the probability theory. So the students normally come across about the probability concepts. So the probability ensures the grid doesn't crash when clouds passes over the solar farms. So in this way, in power systems also, these mathematical concepts play a very important role. The next is the very important topic for the electrical as well as the electronic students, that we call it as digital signal processing and communications. That is, we call in short form as DSP. So here we can see three major concepts. That is, one is the compression, another one is the error correction, and the next one is the noise analysis. So the first we can see how in compression we can use this mathematical concepts. That is, mainly it is used for the JPEG images as well as in MP3 audio. It uses the discrete transforms to discard the unnecessary data while maintaining the quality. So by this way we can get a clear images without any errors. The next one is in error correction also we are using the information theory. So this information theory, it helps the computers to guess the missing bits when Wi-Fi signals are weak and ensuring the correct message delivery. So most of the errors are corrected in this way and we can get a good signal. And the last one we can see about in noise analysis. In noise analysis, the one of the main probability concept that we call it as an Gaussian distributions are applied here. So the probability theory here, what it does means it calculates the bit error rate. In short form, we call it as BER to determine the data transmission limits. So in this way, in this digital signal processing, we mainly use the probability theory. Similarly, the Gaussian distributions and then information theory as well as the discrete transforms. So based upon all these concepts, we can able to make the compressions or the error corrections as well as the noise analysis successfully. And the next concept, we can see how it is applied in manufacturing as well as in the reliability. So here first we can see in the semiconductor quality control. So one of the concept we can see here, it is the statistical process control. In short form, we call it as SPC. This monitors variance in transistor performance across the silicon wafers to determine the manufacturing stability. So in many of the industries that use, that is, this semiconductor quality control are mainly used in this production of the. So the next one is the reliability engineering. In reliability engineering also we can use the probability concept. That is one of the distribution here we use. It is the Wibble distribution. So the engineering students will come across all distributions, that is the binomial distribution, Poisson, and then Wibble, normal distribution, Gaussian distribution, gamma distributions, and so many distributions they will be come across in their subjects. And we can see mainly in Wibble distributions and the statistical tools, it is used to calculate the mean time between the failures to perform the maintenance before the blackouts occur. So in this way, mainly in the industries for the manufacturing units as well as in the production units, we are applying the mathematical concepts here. And the next topic we are going to see how numerical methods calculations are applied here. So normally in numerical methods, we are calculating the values numerically by using so many methods like the Gauss elimination and Gauss-Jordan, Gauss-Seidel methods, Gauss-Jacobi method, and Newton's-Raphson method. So many methods are there, and these methods are applied to solve the simultaneous equations. So students normally mathematically solve all these equations and they are able to find out the solution of these equations. But we doesn't know why they are applying all these things. So one of the main application of this is, it is a power flow analysis. So modern techniques, we can find some approximate solutions to problems which is impossible by solving by using manually. So we cannot solve all these solutions manually or by calculating. So for that purpose, what we'll be doing means we'll be applying the Newton-Raphson method or the Gauss-Seidel method. Not only this, we can use the Gauss elimination methods also or the Gauss-Jordan method also. So all these methods are used to solve hundreds and hundreds of simultaneous nonlinear equations. And this is mainly applied in the power flow analysis. So not only for this power flow analysis, we can use all these solutions in your circuit analysis and similarly in electromagnetic theory and similarly in digital processing. So this numerical methods concepts is the base thing for all the electrical subjects. So that's why we are having this numerical methods in all over the fields. So by this way, we can see the so many applications, how the mathematics are applied in this electrical fields. So the main thing is the mathematics plays a very important role in the electrical concepts with the real world technology. And similarly, it acts as a language to visualize the invisible phenomena like the current as well as waves. And it manages the real world uncertainties in power systems as well as in manufacturing. So by all these things, we can get a good conclusion that the mathematics plays a vital role in electrical engineering. So not only in electrical engineering, we can see the applications of mathematics in other engineering also, like in computer science or in electronics or in biomedical. So in each and everything, so it plays a very important role. So that's why we say the mathematics is the backbone of the engineering field. So I think by this video, we can analyze how mathematics are applied in all these things. So thank you once again. Thank you all.